I'm Alex Maslowski, and this is Trevor Sheik, and we did the Bobcat Auger depth and angle sensor.
So for our project, this is designed to be used by first-time and novice users to create more precise and consistent holes. So on the left side, you see all the holes are different depths and crooked and not straight. We're hoping this will create uniformity for those novice users so that they don't need assistance while they are operating this in case they're by themselves or even with if there's another person with them, this should aid in the consistency of the holes drill.
To work with Bobcat to figure out we're on the same page with what we're looking for in a product, we created this. It's kind of a design matrix. Basically, it's basic requirements for the project that would allow for the creation of what Bobcat ultimately wanted. So we had different things that we rated, different designs that we made on based on different durability, tells the angle, tells the depth, reaches 10 hours operation, can be removed and added in the field. And that was a key component. They wanted to be quickly added and removed. If they wanted to switch machinery or somebody that had higher technical skill didn't need it on the machine anymore. We threw complexity in there and maintenance, cost and accuracy. Obviously, cost is a driving factor. They want to make the most money they can on it, and they have to be able to sell it.
So through Bobcat, they wanted us to create multiple designs so that we didn't just go forward with one without researching other options. So this is the mechanical design that we thought about doing. So we did a mechanical depth display, which we determined to be too weak. It would break if the auger was shifted right or left or forward or backward while it's touching the ground. This bubble level for an angle display, this is a dual axis inclinometer, which we did end up purchasing and was highly considered. And then it was deemed too small for actual use for our final project, or our final inclinometer.
And then we did an electric design. Like Trevor said, we wanted a mechanical design and electric design to try and figure out which one was more feasible for our project. Our original fully electric design would use an Arduino. It would use an IMU, which is a system similar to what's in Wii controllers. It shows levelness, has a gyroscope in it, and other devices to show basically the angle that the thing is operating at. Then we use a laser rangefinder, or we settle on ultrasonic rangefinder. You can see kind of how it would shoot a beam down alongside the auger to allow for getting depth. The electric inclinometer and the electric depth finder would then display into the cab to the user, so the user could just have an interface similar to what's already in any skid steer augers.
So what we decided to do was actually go with a hybrid design. The physical inclinometer was easier to put on and off than an electric one would. The ultrasonic depth sensor was going to be much more useful than a physical depth sensor because, as I stated before, the physical depth sensor was too weak. So this electronic one was going to be much more useful to the operator. This won't require wires running across the machine because the depth sensor was put in a compact case that had its own power, and this would make the design simpler, last longer, and cheaper. And we ordered the parts to move forward with this in about December.
So, like you were saying, why we move forward with the hybrid design is it was going to be cheaper for Bobcat. The electronic systems were going to end up racking up in prices. I mean, as most people know, electronics can get expensive quick, along with the programming. They have to put more time and effort into that, which costs more money. We have increased durability. Like Trevor was saying, we were able to put the ultrasonic sensor into a small, compact design. Therefore, it had its own durability, and then the inclinometer that we ultimately ended up designing had better durability, less maintenance, easier to set up, and we had a good jump on that, and we knew that we could ensure some sort of product by the end of these 2 semesters. So, like we were talking, this is the ultrasonic sensor pictured over here. This is everything that's in it. That case ends up closing, and it ends up being waterproof and just attaches to the auger. The Arduino sketch shows we have a Bluetooth module connected to that, which then sends it to, this is an Android app that we have. It sends all the information there. We have the ultrasonic sensor, and then we have a temperature and humidity sensor to because the speed of sound changes when there's more moisture or different temperatures present, and so that allows more accuracy with the ultrasonic sensor. As you can also see, we measured it running with a multimeter to then spec out a battery. We are running on 9 volts right now. One 9-volt battery will run it for at least 5 hours. It draws 100 milliamps on a standby when the Bluetooth is not connected, and 80 milliamps when it's connected. Basically, you could do a lot of different things as far as battery packaging options. It depends on how long you want to run it for. It has a USB 1 connector that allows you to pull a battery from any USB compact battery system. Also, we have a 9-volt jumper connector that we've used for testing that's also worked. So then we move to mounting the ultrasonic sensor. As you can see here, if you have it mounted directly above or really close to the auger, you do a spill piles. Also, once you get it on an angle, the top isn't connected. It has this turnbuckle system that allows the auger to try to stay level. And so if you mounted it on anything solid, it would then shoot into the auger, no longer giving you a efficient measurement. Currently, we put it on a bearing system that's mounted up on top of the auger. You can see it behind the hydraulic hoses there, and that allows it to be far enough out that can avoid the floor pile. And then also the bearings allow it to remain level no matter what kind of ground you're on. Then it shoots down off there. You enter, set your plane based on the first measurement, and then it will update and tell you how far you've drilled.
Mounting the level display. So as I stated before, this dual axis inclinometer was great, but was deemed too small, too hard to see from the cab. So I decided to make my own out of about 1 inch or 3/4 inch tubing to make a larger version of it. This is what I started with. I put a much clearer oil in this on the final design. This was kind of just the theory behind what I wanted to do, and this is what I got 3D printed parts for and moved forward with. Ultimately, this is what we ended up doing. I put the inclinometer on as well just to show the size difference. This is a little zoomed in from the cab position, but as you can see, the 2 tubes that I put in with level, they're much more visible, much more visible to the operator and easier to see. The curvature of the two right to left levels are the same, so we used that to get our measurements on where to find level, how to mark out how many degrees left or right where we're sitting, and we use the other axis inclinometer to decide level for forward, backwards, how far forward or how far out or towards the cab we would need to go to make these marks so that we can actually see what's going on. Like I said, we mounted and tested this. It functions very similar to the dual axis inclinometer, and it is much larger. Here is a view from the cab as the auger is all the way down and at least 6 to 7 feet in the air. So you'll still be able to see your bubble levels regardless of how far you are when you start drilling. What testing looked like? So from the operator, you can clearly see that those bubble levels are pretty much right in front of you as you start drilling. Here's our marks that we made to actually see what's level, and these little tick marks make it very easy to watch where you're moving as you're drilling, and it's very easy to correct that with just small movements.
Basically, we finished testing up on this first prototype that we've assembled, and we found that obviously there's some issues with it. A big thing that I wanted to switch is the bearing system on the mount only allowed it to move in one plane to center itself. I'd like to move to something more like a turnbuckle and also something more robust. It's maybe a connector like the hose connector on an air compressor that allows the sensor to click in, make it a little more durable, and allow it to move on more planes to get a better, more solid, more perpendicular reading with the ground. We'd also like to make the inclinometer more compact. We thought it was a little bigger and bulky. We'd also like to make something on the auger to allow the inclinometer to hook to ensure levelness. Currently, we just use we square it up with the base of the turnbuckle, which is square, but we'd like to make something added to the actual turnbuckle on the design of the Bobcat Auger that would allow better integration with that. And then change the display, and after the ultrasonic sensor, we'd like to integrate it with the Bobcat's actual system that they have in there so that they can have all the information reading and connected up to that as opposed to on a smartphone like we currently have. Any questions?